Okay, next thing we should speak about is random variable. What is random variable? It's a function. Random variable, let's call it, say, capital X, is a function defined on omega with values in R, some real values. For the sake of simplicity or easiness of using the events and probability theory, the random variable is a very good thing. So this is a function, but the condition that it must satisfy is the following. If the anti-image of some Borel set of B belongs to F, the set of events. Okay, so B is Borel set. Examples. Supposing we are tossing a die, so what are the possible outcomes? If you're tossing a die, so natural random variable is to give numbers. Okay, but we might do something different. Let it be a play. Let's assume we play with somebody. Somebody tells us, if you toss a number from 1 to 4, you have to pay me 10 groszy. But if you toss 5, nothing, nobody pays nobody. But if you toss 6, I give you 2 zlotys. Okay, so in this case, the numbers are converted into money. So in the case of 1, you're losing 10 groszy, so you're losing 0,1 zloty. In the case of 2, you're losing 0,1. In the case of 3, you're losing 0,1. In the case of 4, you're losing 0,1. In the case of 5, nobody pays anyone. In the case of 6, you gain 2 zlotys. So it's a new random variable defined on omega. Another example. Throw a coin 3 times. So what could happen, possibly? All the omega i's are the following. You can have head and head. You can have head and tail. You can have tail first, head second. And you can have 2 tails. Okay? So these are all possible outcomes. So let X be a random variable which calculates the number of heads. So what are the xi values? Here the number of heads is 2. Here the number of heads is 1. Here the number of heads is 1. And here the number of heads is 0. So this way, to each wi, we gave a number. So we have defined a random variable. Probability distribution function. Of random variable x. Okay. Is a function such that for every P Borelian set in R maps probability okay, let me write it down. Probability of x belonging to B is probability of the set of all those omega in big omega such that x of omega is in B. It looks quite confusing, but let's have a look what we have in, for example, this case. Okay, let's continue. Our random variable has three values, minus 0, 1, then it has value 0 or value 2. So these are, say, possible values of a random variable, and now probability that random variable has exactly this value. What's the probability? There are 4 out of 6 possible events, so this is 2 over 3. This is 1 out of 6, so this is 1 over 6. And this also is 1 over 6. Okay, so I hope it is quite simple. So those outcomes are represented by number minus 0, 1. This is represented by 0, and this is represented by 2. These are the values of random variable, and probabilities are the following. So this is the probability distribution function on this random variable. Okay, let's have a look at this example. What do we have? The xi's. Xi's can be 2 or 1 or 0. Okay, so what is the probability that random variable is equal to xi? What's the probability? It's 1 out of 4. This is 1 out of 2, and this is 1 out of 4. Okay? Now, one more definition. So we have cumulative distribution function. Cumulative distribution function, that could be called the probability distribution function, cumulative distribution function, this is BDF, this is CDF, is the following function. F of A is equal to probability that X is not bigger than A. So, let's have a look at our first case. Let's have a look at our first case. And our random variable x given here. Fx of A. Or maybe the subscript x is good to have. So this is probability that x is less or equal than A. So, if A is something less than minus 0, 1, then of course probability is 0. Less than minus 0, 1. Then we have 2/3. 2/3 if A belongs to the set interval minus 0, 1 until 0 open. Then it is 2/3 plus 1/6 is 4/6. This is 4, 5/6, 5 over 6. If A belongs from 0 until 2, and this is open again, and 1 if A belongs from 2 to infinity. Okay, so we just cumulate these values. And we can even have a graph. How about the graphs? How about the graphs of PDF or CDF? So in the first case, the graph is very simple. The graph is very simple. We have minus 0, 1, and we have the 0, and then we have 3 points. Interesting. 2/3 is here, and here we have a dot. Then we have 1/4 here, 1/6 here, and 1/6 here. So this is probability distribution function graph. Okay, now what's the graph of cumulative distribution function? It's more interesting. So minus 0, 1 is important, 0 is important, 2 is important. So it is completely 0 until we get to this point. Maybe I should lose another color. Until here, and open. Then from minus 1 to 0, it's 2/3. And it's open here. Then from 0 to 2, it's 5/6, so it is a little bit higher. And 1 at from 2 to infinity is exactly 1. Okay, so this is the cumulative distribution function. Okay, as an easy exercise, you might do this probability distribution function graph and construct cumulative distribution function for this random variable.